Okay, all right. Okay, so I'm going to continue from last time. So, I mean, the plan at this point, since we have this today and then another couple of lectures next week. So, I mean, the week after next will be the various presentations. So, I'll still be adding a few more things to the web page in the next couple of days, but you can start to actually think about what you would like to talk about, and you just have, when you decided, or if you have questions about it, just send me an email and I'll try to compile some schedule of the various presentations as soon as I get some information from you about. Also, let me know if one of the 2 days is, if you prefer one of the 2 days rather than the other one. I'll try as much as possible to accommodate everybody, but
I strongly prefer to do my presentation on the 4th instead of the 6th, because by the 6th, I will have both of my quality papers.
okay, yeah, just remind me when you email me with your preference, and remind me of the preference of the day, so that I don't forget. Okay, so, but anyway, so the last few things that I want to discuss. So I'm going to finish today this part on the Semiring parsing. There's one more thing that I want to say a few things about, which are the way to think about adjunctions in syntax in terms of the geometry of associahedra, which I've been talking about recently. And then, basically after, which I probably also be talking about today. And the last thing that I want to cover in the class is actually some comparison between what we've seen so far about generative linguistics, about the way that one can think about the structure of language in modern linguistics, and what is happening on this whole story of the large language models that is happening now, and how one compares these viewpoints. And of course, I'm not going to do a class on large language models, since we are flooded with classes on large language models. There's one just before this class, and there's another one just after this class. So I think there's more than enough places where you can learn about them if you want. But the point is here to actually try to compare what the study of language as a structure, as a generative structure that tries to model the way that we handle language in our minds, is related to the way that machines currently handle language. Okay. All right, so that's the plan for the rest of the time. So let me come back to what I was discussing at the end of last time. And as I said, I'm trying to model something that's being used mostly in the context of context-free grammars, namely trying to assign to chains of derivations in a grammar, in this case in the formal languages sense, some kind of parsing in a semiring, either a Boolean semiring or some probabilistic semiring, like the Viterbi semiring, or some kind of more abstract semiring of derivation. So I put on the web page a paper by Goodman on Semiring parsing that summarizes the way that Semiring parsing is done in the formal languages sense of context-free grammars. But here, the model of how the structures are generated is based on our what I discussed, the operation of merge on workspaces. So when one thinks about a derivation in this sense, it means like a chain of merge operations that transforms workspaces and that builds structure in the process by transforming workspaces. So then the question is how one adapts this type of Semiring parsing for chains of derivations in this merge sense. Okay, so as I was saying at the beginning of last time, at first I'm gonna introduce a certain algebra of merge derivations, and I'll do it in a way that is sort of still related to this kind of parsing using characters of algebras that I talked about in in these last few lectures in terms of modeling the syntax semantic interface, and then I'll move on from there to actually getting, a little bit more of this structure on the structure we want on these merged derivations. So, as I was saying, we are seeing this selection of certain forms of merge as preferable in terms of various constraints on how they change the size of the workspaces. And the kind of constraints that we discussed some time ago was one constraint that tells you that your size of workspace is not exploding along the derivation. You should actually try to converge to something that will be a single formed object. So the number of connected components in the workspace that you start with should not increase, so it should be larger than what you end up with, or not smaller than what you end up with. At the same time, you don't want to lose syntactic informations along this derivation, so the number of accessible terms, so accessible terms should remain accessible, which means that the number of accessible terms is non-decreasing. And then there's the minimal yield, means that the balance is as tight as possible, but more generally could be just something that's no negative, meaning that the amount of the growth of accessible terms at least compensates for the decrease in number of components. And there is this other complexity loss, which is the one that says that the components end up inside components of larger complexity and not of smaller complexity along these derivations. Okay, so if one takes these constraints, so the idea is how to build this into selecting which derivations work or not in a way that uses this idea of Birkhoff factorization that we have been discussing for the syntax semantic interface. So a way to do that is to actually make all the possible merge and derivations, all the possible ways that you can build structure using chains of merge operations on workspaces into some kind of algebraic structure. So the simplest way to do this is to say, okay, I take as my basic objects that I'm looking at, all possible ways of transforming one workspace into another one by a certain set of operations of applications of merge, so a certain chains of applications of merge, with whatever intermediate steps you need in order to do that. And so I form like a vector space over these elements and over this set. And then I can introduce a simple multiplication operation that is commutative and associative, which simply takes two separate pieces with their own transformations, combines the workspaces by the product of on workspaces, and combines the operations. So if you have operations that happen separately on separate parts of the workspaces, you can just combine them and make them happen in parallel. And that's what the product means here. So if the product is simply inherited by the commutative associative product of the Hopf algebra workspaces. And so you can further enrich this algebra by introducing Laurent series over this ring. So if I have a ring or a commutative associative algebra, I can form the algebra of Laurent series over this just by introducing a variable and having coefficients of the series in my ring A. And this comes with the Roth-Baxter operator of weight -1, which is exactly the prototype Roth-Baxter operator that is known from the theory of physics, which is the one that projects on the polar part of the Laurent series. So it takes only the part where t has a negative power. And so this is what was the prototype example we use in physics to subtract divergences in one field theory by considering these divergences as Laurent series. Okay, so you can do this with where the algebra A is this one that we just constructed here. So you can, take Laurent series where the coefficients are elements of this algebra. Okay, why do you want to do this? Well, we can construct a character from the Hopf algebra workspaces to this algebra of merged derivations. And this is similar to, if you look in this paper that I put on the webpage of Goodman, Semiring Parsing, they discuss this case where your Semiring parsing happens in this what they call universal derivation semiring, where you have they call the possible derivations in that. And so this is the analog what you want to do here. So what am I describing here? I take a workspace in the Hopf algebra, and I associate to it all the possible ways that I can form that as an object, starting from so these are just the set of leaves of F. So it's just the basic lexical items as building blocks. And I'm looking at all the possible ways that I can go from here to here by a chain of merged derivations. And so that's it associates to a workspace its generative process under merge. So the way that you can obtain it starting from a completely disconnected set. Okay, so and this is manifestly a character of algebra in the sense that we use several times. So this means that it's a morphism of commutative algebras. And of course it is, because if I take the disjoint union of two workspaces, and here I'm taking just I also take the disjoint union of their sets of leaves, and whatever derivation happen in parallel on the two sides, I can put them together as a single derivation acting in parallel. Okay, so this is a character in our sense. We can also, so this is with value just in this ring of merged derivations that I described a moment ago. But you can also slightly modify this character to make it take values in this Laurent series over this ring of merged derivations. And for example, I can do this. So I can not only keep track of what are all the possible ways that I can assemble F, starting from the disconnected set of its leaves by a chain of actions of merge, but I can also weight the total effect that this has on the size of the workspaces in going from here to here. So how well this delta would be one of these measures, either number of connected component, number of accessible terms, of the combination of the two. And so this is again a morphism of commutative algebra here. However, the thing is that if I'm looking just at this entire series here, I don't actually gain all that much by introducing this counting here. And the reason for that is because here I'm just taking this entire chain of derivation where I start from just the leaves as completely disconsoled, the set of lexical items with no structure, and I go all the way up to completing the structure that I'm looking at. And I'm just looking at the entire complete effect of this from so the beginning of the end of the derivation. And if I do this, the point is that I can just count how this this counting of the change of the size of the workspaces behaves. But I mean, if I start just from the disconnected set of leaves and I get to, well, let's say a single component that is a tree, then all of these will always be positive. So this will always take values in the convergent part of the algebra of Laurent series. I never get any negative power here. So this means that, okay, there's no interesting factorization going on. This is already fine. It's always conversion. And this is because I'm just looking at the entire chain of derivations all at once. But the point is that when I'm thinking about these changes on the size of workspaces as some kind of constraints, I want to think of them as constraints over the individual steps of the derivation process, not just over the entire chain of derivations. So here, what I'm saying is that if I evaluate them over the entire chain that goes from a completely disconnected set of leaves to a single connected component of the tree, these will, will always, be okay. But this doesn't prevent at some point during the process to have some steps that are not okay. But I can do slightly better than this if instead of just focusing on the entire composition of all the possible derivations from disconnected leaves to fully formed tree, I look at all the intermediate steps. So I form a character which does not just have a single terms from LT to T, but just looks at all the possible intermediate steps. And for each one of them, it counts the effect on the size of the workspace. And now this might be able to detect whether at some step along the way I'm violating some of the constraints or not. And so in this case, you actually now do get something which has a priori also a polar part, when you in some cases will not have one because you always go to transformations that don't violate any of these minimal yield constraints. But in some cases you will have a polar part. And so you can form, now you can do this same process that we have seen several times of actually doing this inductive factorization of your character into the part, the divergent part and the renormalized part. And in this case, what is happening is that when you take this, so with this Bogoliubov preparation with respect to the Rota-Baxter structure that is the projection on the polar part, what you're doing is you're analyzing in parallel all the merged derivations of all the accessible terms of your final structure T. And you want to ensure that all the undesirable forms emerge, the ones that violate some of the size constraints, they get progressively removed by this renormalization process, so that at the end, you're left with only the derivations where you never violate any of the constraints. And the way that this works is that you can. So when you take the projections, this is the projection on the non-polar part. So this projection on the regular part, the projection of what remains that does not violate any of the constraints. And this is again not the same as just projecting the entire character that you start with, because that would not necessarily cancel each term one at a time, but you use this inductive procedure of the Birkhoff factorization to correct terms one by one by looking at all the substructures. So more in detail, what is happening here is that suppose that you have a term in the sum that describes this overall character. So there are some intermediate steps in this chain of derivations that violate some of the constraints. Then the corresponding forest where that happens, so the corresponding step that you obtain where this violation happens, is an accessible term of the final resulting tree. So there will be some terms in the coproduct where that accessible term is extracted. And so there will be a corresponding term which uses that accessible terms that's detected here. And when you form this corresponding term, remember that this subtraction, so there is this term that has the subtraction of the polar part. And so these terms will subtract from this piece exactly the part that contains the divergent term. So this will have the effect of removing this unwanted derivation that violates the constraint, whereas all the terms that don't violate are sent to zero by this projection that's involved in this this psi minus pi. So they will not produce a term that cancels them. And so you will be left at the end with the terms that don't violate, only with the list of the terms that don't violate any of the constraints, which is exactly the way that the divergent parts of the Feynman integrals are removed by the renormalization process. Okay, so this is a way of revisiting this separation of the merge operations into the internal external merge and the other forms of merging. You can do the same with this no complexity loss kind of constraint, and again do the same thing, form a character. Now the situation is slightly different, because you have to verify this constraint on each of the components of the workspace by looking at where the root of each component ends up, knowing which other component. So you're gonna have multiple variables that keep track of the different, the different lexical item, and each time in which component they end up. And so it's like a multivariable version of the same story that I just said. You have a Laurent series in several variables, and you are removing the polar part in each of the variables. But the argument is exactly the same, that any term that produces a violation of this constraint will be removed, and by this inductive procedure of renormalization. And at the end of, you will be left only with those, terms that don't violate any constraints. And so in the end, you will be left only with chains of derivations that contain only external and internal merge, and don't contain any of the other forms of merge that can violate constraints. Okay, so now, I'm gonna kind of use this as an intermediate step to get a little bit more into this idea of semiring parsing. So when I describe this algebra of merged derivations, let me just come back for a second to the definition that I gave here. Yes. Okay. So the way I describe this algebra of merged derivations is very simple, in the sense that I'm taking chains of compositions here, but my product in the algebra is just this parallel version, right? Anything that acts in parallel on different parts of the workspace, and that's why it gives me a commutative product, because I can apply them in whatever order. But I'm not considering as part of the product in this algebra the composition of. I mean, if you want to, okay, you can say this is a special case of composition where I'm composing things that act on completely separate domains, and so it doesn't matter how I compose them. But I don't actually include the actual compositions that act on the same, where the source of the next is the target of the previous one. I don't include that as part of the product in this thing. So it's a kind of well, it just serves the purpose that I showed a moment ago, and this simplified form of product that only looks at parallel operations is enough to be compatible with the Hopf algebra product of the Hopf algebra workspaces, so that I can form, I can easily form characters of the Hopf algebra. But now, of course, if you want something a bit more elaborate than this, where you actually follow the composition of derivations. And of course, if you do that, then you immediately lose the fact that the product is commutative, because the composition of functions is not a commutative product. So you get some structure that's looking different from this. And in particular, it's not quite reflecting anymore the Hopf algebra workspaces, which is a commutative Hopf algebra. So what are you, seeing? What is the actual algebraic structure that is going on if one looks more carefully at this type of composition of derivations? So let's just may step back to something that I said a while back, that if you have a commutative Hopf algebra, it is the same as functions on a group. The group scheme that is dual to the commutative Hopf algebra. So if you take a homomorphism of commutative algebras from the Hopf algebra to a field or to another commutative algebra, that those, if your Hopf algebra didn't have a coproduct, that would be just a set. Because it has a coproduct, it has a multiplication, and because it has an antipode, it has an inverse, and so it's actually a group. So commutative Hopf algebras are functions on a group, group scheme, because you can choose your target algebra for the morphism. Okay, so the idea then is, that you can generalize from a group to a groupoid. The difference between a group and a groupoid is that in a group, you can multiply arbitrary elements with each other. In a groupoid, you're composing arrows. So you can only compose two things when the first arrow ends where the second one starts. And so a group is a groupoid with a single element. So all the arrows start and end at the same place. And so you can compose everything. And so you can say, okay, if a Hopf algebra is functions on a group, what is it that is functions on a groupoid? And that's something that is called a Hopf algebroid. Makes sense, right? Okay, so what is such a thing? All right, so let's kind of unpack the definition of what is a Hopf algebroid. Okay, so it's not a commutative algebra, but two commutative algebras. Why is it two commutative algebras? Why do you need two commutative algebras? Because, so remember that I can think of a groupoid also as a category where all the arrows are invertible. The objects of the category are, the points where the arrows can end or start, right? And the morphism are the arrows. Okay. So I have two things. I have a set of objects and I have a set of morphisms. And each one of them has functions on them. So I have two commutative algebras, functions on the objects and functions on the morphisms. Okay, so that's why I need a pair of commutative algebras. Now, so functions on the objects, functions on the morphisms. Now, of course, these have to talk to each other, right? Because morphism starts somewhere and ends somewhere. So every morphism has so there are two maps from the set of morphism to the set of objects, the source and target map that tells me if I give you a morphism where it starts and where it ends. So I have two sets, morphism and object, two maps from morphism to objects, source and target map. Maps on algebras of functions go the other way around as opposed to maps of the underlying sets. Okay, so if I have source and target map from the set of morphism to the set of objects, I have two maps from the algebra of functions on objects to the algebra of functions on morphism, source and target map. It's composition with your function composes with the underlying function on sets. Okay, so I have two morphisms, source and target, from the algebra of functions over objects to the algebra of functions over morphism. And in particular, you can think of these two functions as giving this algebra the structure of a bimodule over this algebra. Because everything, all these algebras are commutative, so I don't have to worry about no left and right action. But if I give you a morphism of algebras, in particular, it gives me a structure on the target algebra of module over the other one. Because how do I act with the first algebra on the second? I take the map and then I multiply in the target. Right? So that gives me the structure of a module. And I have two maps, so I have two structures of a module, so I have a bimodule structure. Okay, so here's the first part of the structure. Now there's something else with morphism. Morphism can compose. So I have a composition of morphism, and because it's a category, the key definition of being a category is that the composition of morphism is associative and that it has a unit morphism over each object. Okay, so I can compose morphism. So this means that if I'm looking at functions on morphism, this composition product of morphism becomes a decomposition of functions on morphism, and so it becomes a coproduct on functions on morphism. Okay, so I'm going to have a coproduct, and that takes some function on morphisms and decomposes it, as bimodules over the algebra of functions on the objects. And this condition here is exactly the fact that it's telling me that my composition of morphism requires that the target of the first morphism is equal to the source of the second morphism. The maps here are exactly the source and the target. So this tensor product over A0 is the one that enforces this requirement that the composition only happens when the source and target match. Okay, so that's why it's a tensor product over the action of A0 and not just over the underlying field. So this is the composition of arrows in the groupoid. And now, I mean, there's the actual key properties of groupoid, which is the fact that all the morphisms are actually invertible. That's what makes it a groupoid. And so you want an inverse on the arrows, which means that you have a kind of conjugation on functions on the arrows, which is composing with the inverse. And this is the antipode function on this. Okay, so this is a Hopf algebroid, so functions on a groupoid. There's you can introduce a slightly weaker notion, which is a bialgebroid, which is simply everything the same, but you don't require that the morphisms are necessarily invertible, so you don't have these antipodes, you don't have the S. So what is that dual to? Well, it's dual to a semigroupoid, which is just a fancy name for a small category, because now you simply have objects and morphisms compose in an associative way, but you don't necessarily have that the morphisms are invertible. So this is just a small category. Okay, so a bialgebroid is functions on a small category. A Hopf algebroid is functions on a groupoid. So there's a few additional properties that I haven't listed yet, which has to do with the unit and the compatibility of with the coproduct and so on. So let me just finish up what all the compatibilities should be to make everything work the way it should. So there's a co-unit that goes from the algebra of functions on morphism to the algebra of functions on objects, and is a morphism of bimodules, where this is seen as a bimodule over itself with its own. And it's so this is the fact that guarantees that you have a unit morphism attached to each object. Because if you go the other way around on the underlying objects, it's a map from objects to morphism, which says that to every object there's a special morphism attached to every object, which is the identity morphism. And it has a compatibility there's a compatibility between the co-unit and the source and target map, which is just saying that the identity morphism has the same source and target, which is just that. And the compatibility between the co-unit and the co-product is simply saying that composition with the identity morphism does nothing. That's the way that either composition with the identity on the source or composition with the identity on the target does nothing. And there is the condition of associativity of the composition of morphism. And then there is the fact that the inversion of the fact that the morphisms are invertible, the corresponding S is in involution as the inversion is. And if you invert an arrow, you switch its source and target. Right? The inverse arrow has the opposite source and target. Okay, so this is what the usual properties of composition of arrows, then translated in terms of this, the effect on functions on morphism and objects. And yeah, so composition of a morphism with its inverse is the identity, which again is just you have to rewrite it in terms of co-product and product and antipode, and the co-unit and the target and co-unit and the source. That is, if you follow what this means, right? Co-product is composition, the inverse, the antipode is the inverse, and this is just exactly saying that the composition of a morphism with this inverse is the identity. And you have the as I write in it here, I'm also using this fact that you have a kind of multiplication as well as the co-multiplication, and it's so it just extends. Well, so we know already that H1 is an algebra. Right? It is the algebra of functions on the set of morphisms. So as an algebra, it has its own multiplication, and which is just a pointwise multiplication. But this is over the underlying field, But you can extend this to a multiplication that is compatible with the action, the bimodule structure that's coming from the source and target map. And this is nothing really, just saying that if I'm multiplying pointwise, I'm preserving the source and target of the morphism. So, okay, so the other properties that are listed in these definitions of Hopf algebroids is the fact that the source, if I take so this is another obvious fact, when you think in terms of what it's saying about compositions, if I take the composition of two arrows, the source of the composite is the source of the first, and the target of the composite is the target of the second that apply. It starts wherever the first starts, and it ends wherever the last ends. Right. And so when you write this out, it gives you a relation between the co-product and the source and target homomorphism, eta S and eta T. Okay, so this is Hopf bialgebroid. By the way, this definition of Hopf bialgebroid was actually introduced by Ravenel in the context of algebraic topology already, quite a long time ago. And one can also define what a morphism of algebroids is. And of course, it's just dual to an underlying morphism of groupoids. So you have morphism of algebras, so a pair of morphism of algebras for both the algebra functions on objects and the algebra functions on morphism. And then you want compatibilities of these functions, of this morphism, with all the rest of the structure. So they should intertwine, the co-units, the source and target, morphisms, and the antipode, and the co-product. So then you should carry over the entire structure, along with them. So there's nothing special here. Just carry all the structure. You require your morphism to carry all the structure. Okay, so this is what we want to use if you want to keep track of compositions of arrows, right? And so in particular, this the replacement of what is used in semiring parsing, so for context-free grammars as the derivation forest, so-called derivation forest, would be here this bialgebroid of merge derivations. I'm saying bialgebroid rather than Hopf algebroid because we don't really have anything that strictly depends on the antipode in the action of merge on workspaces. It does depend mutually on the co-product, but it doesn't explicitly use the antipode. So in a sense, it's really depending on the bialgebroid structure rather than on the Hopf algebroid structure. So the way these bialgebroid of merge derivations work. So I have to give you this data, right, that I just described. So the first algebra A0 is the polynomial algebra generated by the workspaces. So it's the same as our Hopf algebra of workspaces, but where I'm forgetting the co-product. I'm just taking this joint union of forests as product, and just functions on the vector space generated by the forest with the product given by this joint. And the algebra of functions on morphism, so these are the algebra H1. I take this algebra of merge derivations that I just described before. So this one that looks at all the possible chains of merge derivations between two workspaces, and again with this product given by this joint union. Okay. So now, I mean, the product of these algebras is still this commutative product that's just given by this joint union of forests and by parallel applications of on different parts of the workspaces. The part that will take care of the actual compositions is going to go in the co-product here. And but so far, these are like my two commutative algebras that are that determine the objects of morphism of my algebroids, right? So it's just saying, well, this is what they're supposed to be. Like, all objects are the various possible workspaces, and morphism of arrows that go between them that are applications of merge operations, right? And the left and right module structure, I mean the bimodule structure that correspond to the source and target is just the obvious thing. So you look at you fix you pick a particular workspace, and you look at a possible merge derivation, and if your workspace is the source of that operation, then you just this is just the identity on that operation. And if it's not, and it's zero otherwise, if it's not the correct match of source, and similar on the other side, if it's the target, then that is the identity on that, and if it's not the target, then it's zero. Okay. And the co-product is just the compositions, or all the possible ways of splitting a particular derivation into a composition of pieces. And so you get all the possible compositions of a chain of merge derivations, followed by another. So it looks like, if I write it like this, right, it looks like I have lost something because, in the part where the workspaces are, which is in this data is 0, I'm only seeing the algebra structure, and I no longer see the co-algebra structure, right? That I know that was a Hopf algebra, but now I'm sort of lost the co-product there. But the fact is that I haven't really lost it because the set of arrows that are now the merge actions, the coproduct is built into this merge transformation. So I've only repackaged it somewhere else into this structure. I no longer view it as part of the structure that I have on the set of objects. I'm going to see it as part of the structure that I have on the set of morphisms. So it's yeah, but the overall information that I'm keeping track of is still the same. Okay, so now this is what replaces the Hopf algebra. The Hopf algebra has become a Hopf algebroid or a bialgebroid. Now, what we've seen up to now about these parsing situations is that we take a character from a Hopf algebra to some kind of Rothe-Baxter algebra. So the Hopf algebra has become a Hopf algebroid. The Rothe-Baxter algebra is going to become something itself, a Rothe-Baxter algebroid. That's the name of the game. So we can keep playing it. And so, of course, I have to put a warning about terminology here, that if you look for algebroid, you find several different uses of the term algebroid in mathematics that are not equivalent. So the one that I'm using is just the one that's motivated by the definition of Hopf algebroid that I just gave. And I was saying, okay, Hopf algebroid is functions on the groupoid. A bialgebroid is functions on, well, a semigroupoid, or in other words, a small category. And what is an algebroid? Well, it's functions on what? Well, the last thing that I can lose is the compositions, right? Because in a groupoid, I have arrows that can always be composed. I mean, can be composed when source and target smash, but can always be inverted. In a semigroupoid, well, they can no longer be always inverted, but they can still be composed. And in an algebroid, well, maybe they cannot be composed. So what this means is that I'm looking at functions on a directed graph, okay? Because if you are just on a directed graph, you still have, in a sense, source and targets. You still have a set of vertices, which is your source and targets. And you still have a set of edges which go between sources and targets, but you no longer have necessarily the fact that if I have, an edge that goes from vertex X to vertex Y, and an edge that goes from vertex Y to vertex Z, I don't necessarily have an edge that goes from X to Z. Whereas in a category I do, because in a category I can always compose morphism if the source and target match. So this is the difference. So in this setting, it's the natural thing to consider as the definition of an algebroid is simply something where, so what do you retain at this point? You keep the fact that you have two commutative algebras, one as functions on vertices and one as functions on edges. That you do have two morphisms of algebras that make E into a bimodule of A. And these are just the fact that edges are going to have a source and target. That's still true. And you still have so you still require to have a co-unit that's compatible with this source and target. And if you want, you can think of this as still thinking that you have a trivial identity morphism at at each vertex. So you can think of it as a graph that has always has one looping edge at each vertex, which you can kind of forget about it because it's always there. Okay, so right, as we can think of this as this data, right, the data that I just described here, which is what I'm going to call an algebroid, is dual to a directed graph scheme, which is like you have Hopf algebra dual to group schemes, commutative of algebra dual to group schemes, commutative algebroids are Hopf algebroids are dual to groupoid schemes, and commutative bialgebroids are dual to semigroupoid schemes, and these are directed graph schemes. So what I mean by that is that if you choose any commutative algebra R and you look at the set of morphism of commutative algebras from A to R and morphism of commutative algebra from E to R, these are sets, right? They're just the set of morphism. And you can view this as the sets of vertices and the sets of edges of a directed graph, where the source and target maps, which tell you which edges are attached to which vertices, are exactly dual to this morphism of algebras. And this, if you want, is the definition of what I mean by a directed graph scheme. Whenever I give you a commutative algebra R, I get a directed graph by this corresponding set of vertices and edges. And we assume that you have this identity morphism. Okay, so you see that then the way that you can revisit the case of the bialgebroid and the Hopf algebroid is by saying that the bialgebroid is also a directed graph scheme, but is a graph that satisfies reflexivity and transitivity. Okay, so the transitivity is exactly the fact that you can always compose morphism, and reflexivity is the fact that you always have one morphism at each. And the Hopf algebroid is the case where the graph is also a directed graph scheme, but for a particular kind of graph that satisfies reflexivity, transitivity, and symmetry, which is now the invertibility of the morphism. Okay, so this is like the picture of this different level of structures and the way that they are related to each other. And so now what about this Rothe-Baxter type of structures? So what happens to these? So remember that these Rothe-Baxter operators are some kind of projections. And they are projections that are not just, as projections, they're linear maps, but they have this particular property that the range of the projection is not just a linear subspace, but is a subalgebra. And so now you have the only thing that you have to slightly enrich this definition of a Rothe-Baxter operator with is the fact that you don't have a single algebra, but you have a pair of them with this source and target map between them. And so so instead of just saying that your R Rothe-Baxter structure is a linear map on your algebra, now you think of it as a map that also has a kind of module structure, is compatible with the module structure. And the most general way in which you can make it compatible with the module structure is by saying that it's not just a linear map, but if I act with the algebra A on E through the source or target map, then so a priori I could make it stronger by just saying that I pull out HS of A, but I can allow more generally for some transformation of the algebra A that implements this factor. So this is not where this is not necessarily the identity. It's some either automorphism or endomorphism more generally of the algebra A, and similarly for the target map. And also you want the compatibility with the co-unit. And then the main Rotobuster identity remains exactly the same. So it's exactly saying that if I multiply elements in the range of the Rotobuster operator, you still get something which is in the range. So the range is actually a subalgebra. There's a slight normalization condition, difference with respect to the Rotobuster algebra case, because in the Rotobuster algebra case, it actually does follow that the unit of the algebra is either mapped to itself or to zero by the projection. In this more general case of these bimodule structures, you actually have to impose it as an additional condition. So the main source of examples is in fact simpler than this general definition. And the main source of examples for this kind of Rotobuster algebroids is functions on a directed graph. So E would be the algebroid is functions on a directed graph. So would be functions on the edges of a directed graph with values in a Rotobuster algebra in the usual sense. And so the Rotobuster operator is just acting as on the coefficients of the functions. So the functions on the graph, but taking values in some algebra that happens to have a projection, which is a Rotobuster operator. And so in this particular case, this part of the transformation is just the identity. So there's no action on functions on the vertices itself. And on functions on the edges, you just have the Rotobuster operator acting on the coefficients, and so this is the simplest class of examples that are actually mostly sufficient for all applications. Okay, so next thing in this game of the oidification of algebra. So the terminology gets more and more ridiculous as it goes. Is semiringoids, because as we've seen, very often instead of taking wanting characters that take values in an algebra, you wanted to take values in a semiring. And so the analog of an algebroid becomes a semiringoid, which is, of course, by now we know the whole game how it's going to work. It is a pair of commutative semirings with semiring homomorphism that correspond to source and target maps. And that gives the structure of a bi-semi-module over A, which means two representations of a semiring. And you have the unit, which is a bi-semi-module homomorphism, compatible with the source and target map. And of course, once you have a semiringoid, you can have a Rotobuster semiringoid of y plus 1 or minus 1, where you do exactly as before. So it's really a Rotobuster structure on the set of functions on morphisms, which, again, has the same properties that I just described, but with respect to the semiring operations rather than the algebra operations. Okay, so the point of all this exercise in oidifications is that you can extend in exactly the same way as the usual proof, the inductive construction of the Birkhoff factorization in algebroids and semiringoid. So if you have a morphism of algebroids from a Hopf algebroid to a Rotobuster algebroid, you can use exactly the same argument that we have seen for morphism from Hopf algebras to Rotobuster algebras to split out the morphism into two parts, a sort of positive and negative part with respect to the two sides of the Rotobuster decomposition of the target Rotobuster algebra. that are determined by the coproduct on the Hopf side and the Rotobaxter projection on the Rotobaxter side. So this extends in the same way. So okay, what does it mean? That's at this point, after all these gymnastics, what is this actually good for? Well, the point of what we are actually describing. As I said, an algebroid is just functions on a directed graph. And so if I define a morphism of algebroid, which is the one that the analog of the character of the Hopf algebra, right? If I define a morphism of algebroid, it means that dually I have a map of graphs. Right? So I have a map of graphs from some kind of, let's say, template graph, which is the one that's dual to my target, Rotobaxter algebroid. So I'm choosing some kind of template graph, and I'm mapping that graph to the graph that also is a category, which is dual to my, this is actually a groupoid dual to my Hopf algebroid. So what does that mean? It means that I'm looking at a particular template of a diagram of arrows inside my category. So I'm looking for particular schemes of derivations where I am specifying the diagram that I'm looking for. Right? So it's like saying that I'm assigning a diagram in a category, right? Assigning objects and morphism between them. And of course, these are not things that can be composed in G, but I map them to some place where they can be composed. And so, for example, if I look at an arrow in the groupoid, what is this Bogoliubov preparation with respect to some character like this? And let's say with the trivial Rotobaxter structure, that's just the identity. Well, what I'm doing here is I'm taking an arrow in my groupoid, and I'm looking at all the possible ways of obtaining it as compositions of edges in my template graph. So all the possible ways of obtaining these transformations as compositions of some pre-assigned set of transformations. And in particular, I can assign not just these transformations, but with particular weights that depend on this Rotobaxter structure that I have on the target algebra. And so, for example, I can get, for example, if I want a template where certain transformations have a higher probability than other assigned a priori, these are part of the data that go here. And I can use that to select transformations in my actual ring of my actual Hopf algebroid of transformation, my actual groupoid. There, I can select those that will correspond to maximizing the probability in my template. Okay. So that's what this type of parsing is doing for you. Right? It's not just it's parsing with respect to particular models that you choose, which are given by your choice of graph and your choice of weights on that graph that correspond to this Rotobaxter structure. Okay, so for example, right, if you in this case of merged derivations, you can take your target with target functions on a graph with values in some, for example, tropical semiring with this kind of ReLU threshold, or Viterbi probabilistic semiring with some other kind of threshold. And then this character from the Hopf algebroid to this Rotobaxter semiringoid will assign, we look at possible diagrams of merged derivations that are modeled on a particular diagrams, and that will consist of compositions coming from this chosen diagram that are weighted in this given semiring, filtered by this Rotobaxter structure. So, for example, in the case of the ReLU, you look at possibilities where all the weights are above this ReLU threshold, or all the probabilities are above this given threshold, or if you are in a Boolean semiring, where the certain truth values assignment is holding at all the steps in the derivation or not. Okay, so this is, for example, you can look at all, if you have like a chain, this is like a simple chain of merged derivations that builds a structure starting from its disjoint union of lexical items. And your template graph is just a simple, say, composition of two arrows. And so you're looking at all the double compositions in here. And depending on which weights you have assigned, you can look at only those that have a certain threshold of assigned to the weights assigned to them. Okay, so this was something that I marked about this. And let me now get to the last topics that I want to discuss. Okay, so this is something that actually, I wasn't completely sure where to fit it in, but I mean, it goes back to something that's related to this geometry of associated that I talked about recently. So I think I'll just discuss it here. So adjunctions are kind of a particular as part of sentence structure that one encounters frequently. So I know that when I was a child, in Italy, there was a little song that basically was telling the story. It was started like this. The beginning of the song, it was said, my father bought a mouse at the street fair. And then the cat came that ate the mouse that my father bought at the street fair. And the dog came that bit the cat that ate the mouse that my father bought at the street fair. And the stick beat the dog that hit hit the dog that bit the cat that ate the mouse that father bought. And the fire burned the stick and the water burned put out the fire that burned the stick and so on. So this is our adjunctions. This is why adjunctions work. You can create these arbitrary long cascades of structures that you can keep adding indefinitely, right? Yes.
Oh, I think there's an English analog of this, it's a story called The House That Jack Built, and it also just stacks on top of each other.
Right. Yeah, that's right. So there's a lot of this stories that and you can make them become as funny as you want with all with an arbitrary long and of course children usually like those very much. So that's the way adjunctions work. And the thing that you can see from these examples is that unlike arguments of the predicate, which we have discussed when I discussed theta theory and this kind of colored opera type structures, the predicates have like a certain valence that requires a certain finite number of arguments that necessarily have to bind with them, like for example to give something to someone. So there are three roles: somebody gives, somebody takes, and something is being given, right? And but the arguments have a pretty tight structure that is finite and strictly regulated by the assignments of theta roles, and that is part of what the external merge does. So we've seen the building of the building of structure through external merge is also assigning pairing the theta roles. In the mathematical sense, one can encode that, for example, in this structure of colored operas or operadoids, given the theme of today. But adjuncts are completely different in the sense that first of all, they are not necessary in any sense. So there's nothing that necessarily carries the calls for adjuncts, and they can be there or not be there. And also, for example, if you take a verb, you can take, it can only take a finite number of arguments, but it can take an arbitrarily large number of adjuncts. Exactly this kind of cascading series of adjunctions. Also, there's another aspect in which adjunctions have a curious behavior, in the sense that they typically can give rise to this kind of structures that, when you assemble them together, they don't necessarily have a well-defined head function, or where the actual head of the whole structure goes. And this, it is also related to the question that, when the model that I was describing about how you map syntax to semantics was always based on having a head function and following where the head of structure is going, and building the image of syntactic objects in semantic space on the basis of what the head function does. Or more generally, the structures related to the head, like spec head and complement, but still based on the existence of a head. Okay, so there are some kind of questions around modeling the behavior of adjunctions. And one of them is, if you look in the linguistic literature, it's often referred to as the problem of invisibility of adjuncts to syntax, or the fact that adjuncts are opaque to syntax and opaque to movement. And these are also called adjunct islands, in the sense that they are not moving according to internal merge in the way that the rest of the structures are, precisely because they're sort of loosely connected to the overall structure. And also this problem of the head is sometimes addressed by, so this is called the pair merge problem, how you actually label this type of headless structures that come from adjunctions. And you want some kind of asymmetry between the way that, these chains of adjunctions are clearly very asymmetric as a form of trees. And so where is this asymmetry coming in, considering that the old mechanism of merge that we have described is intrinsically symmetric, is based on this commutative magma of syntactic objects. Okay, so how does one view some of these issues in the context that we are looking at? Well, so this pair merge proposal, some people had suggested a possible way of thinking of this way of introducing these asymmetries by thinking of these as some kind of two-peaked type of structure. There's some structure that is actually labelable, but then there's a bunch of adjuncts, and instead of writing them as trees that continue, one could think of them as being really separate trees that can somehow combined in some non-standard way, like this. So this proposal is not very nice, in the sense that if you want to really argue that you do have to include structures like this, you have to explain how they're generated. And the old mechanism of merge that we have described does not generate things like this, because you never have merging at the leaf. You always have operations of merge. Even if you include this kind of insertion of Lie algebras and so on, these things would not occur even there. So you have to cook up an entirely different mechanism for justifying this kind of two-peak structure. On the other hand, you could still argue that this is really something that's happening. It's not part of the generative process. It's something that's more happening when you map things into your semantic space, and the actual structures are separately things that are generated by syntax, but they're kind of mapped in a way that they're going to overlap in there. And so this would, in a sense, justify this invisibility to syntax, because if it's something, if this gluing is something that happens in the image inside semantic space, there the computational mechanism of syntax is not present there. It's somewhere else. So the actual computational mechanism of syntax will simply not see these structures, and this could be a reason why they are opaque to the computational the computational mechanism of syntax. On the other hand, I mean, there are other proposals that about how to resolve this pair merge structure that are maybe more more suitable. There's a proposal by Hybrid that describes these pair merge, these asymmetry of pair merge in terms of combination of internal and external merge without cancellation of copies, something like this. So this I'm not necessarily that this type of two-peak structure is necessarily the good answer. In have taken place in a semantic space rather than on the syntactic side. But the question that is more more interesting is another question that's been considered several times in the literature, which is trying to characterize what is the region of the hierarchical structure of syntax that can be populated by adjunctions. Like what is the actual generative powers of adjunctions? Because of course, if you think about a very simple chain of adjunctions, where you get these comb-like trees that are very special, they are very asymmetric, and so you would expect that these are not going to be occupying a very large region inside all the possible structures that you can generate. On the other hand, this is a little simplistic because adjunctions the various pieces of the adjunction can have their own substructure. Like like in the example of the little story, each piece has its own substructure. So they're not necessarily just a comb-like tree. There's something that has something more into it possibly, and so it becomes a slightly more more sophisticated question to characterize what is the generative power of adjunctions. Okay, but on this, at least one can say that there is a complete answer that you can give that is based on the geometry of associaedra. And so, yeah, this is like the simplest type of chains of adjunctions, right? They would look like comb trees like this, or you could start with a certain structure and then start appending adjunctions. On the other hand, right, you could also consider the case where some of these parts that are appended to the adjunction are their own structure inside, so they're not just the comb trees. But so a way to try to locate where these things are is by putting a bit more of trying to compare the way that trees look like one with respect to another. And so here we are assuming that the trees are already planarized. So we are dealing with structures after externalization. So we can look at where they stand on these associaedra that describe different planarization of trees. And the key structures that you can use to describe where the adjunctions stand in terms of the overall number of trees are the Tamari order or the Tamari lattice on planar binary rooted trees, and certain operations introduced by Laudet, which are called non-commutative sums of trees. Okay, so let me explain first what the Tamari order is. So we're dealing with planar binary rooted trees. So we can look at the one skeleton of the associaedron. So we fix a certain number of leaves, right? So we look at all the planar binary rooted trees on a fixed number of leaves. And we can, so vertices of the associatron are all the possible planar structures. And we say that there is an oriented arrow between two of them. And whenever one of them cannot be obtained from the other, by moving one edge from the right to the left across a vertex above it. Okay. And of course, the comb trees, the two comb trees that are like all of it like this, or all of it symmetrically on the other side, are the two extremes of the Tamari lattice. And all the other trees are obtained by a bunch of moves from these ones. So here's the picture of what the Tamari order looks like. So if you have 4 leaves or 5 leaves, in the case of 4 leaves, so this is a pentagon. I mean, this is the associahedron for 4 leaves is a pentagon. And the 2 extremals of the Tamari order are the 2 comb trees. And then each of the other ones is obtained by one move of this kind, where you flip something from one side to the other across the vertex above it. And you have here you have different possible moves that do that. And in the case of 5 leaves, the Tamari order looks like this. Again, the 2 comb trees are the top and the bottom of the Tamari order. And all the other arrows are exactly all the moves that you can do for going between one and the other. So as you see now, the kind of picture that you get is a little more interesting than in the case of the pentagon, but this is the structure. Okay, so this is what the Tamari order is. Now, what are these Lode operations? So when I discussed a little while ago the comparison between the old minimalism and the new minimalism, I introduced the Laurent algebra of planar binary rooted trees. And that was based on 2 operations on trees, which were this over-under operation. However, this would correspond to, like, for example, here, I'm taking this tree, I'm sliding it down this tree until I reach the rightmost leaf, and then I append it there. And here I take this tree and I slide it down that tree until I reach the leftmost leaf, and then I append it there. Okay. And the thing is that these operations are always related in this way with respect to the Tamari order. So there is a relation between these 2 operations and the Tamari order. And so this fact makes it possible to define an operation of combination of 2 trees, which is what this one that they call the non-commutative sum of trees, where you combine 2 trees by taking all the ones that are intermediate between these 2 operations in the Tamari order. And you take the union of all of them. And so this is actually a non-commutative sum of trees. And it is associative, but it's non-commutative. And it distributes with respect to unions. So I'm going to finish this, but I just want to give you an example. So if I take these two trees, then the sum in one order of these 2 is the union of these 3 possibilities, while if I take the sum in the other order, it's the union of these 2 possibilities. Okay, so I'll continue. I'll finish this next time. No, I won't take all that much left, but then I'll start talking about this last topic that I want to cover, the comparison with large numbers.